Hi, I'm Tim Liptrot. With me are
Hagenbuch
and Simon Gilbert.
We've been doing research with Oberlin College as a part of the NanoGrav collaboration. Our research concerns the detection of gravity waves. Gravity waves were first predicted by Albert Einstein. They're ripples in the curvature of space-time created by massive objects. They're very difficult to detect because they're they interact very weakly, and they should manifest as sinusoidal variations in the distance between objects and events.
All right, so how we're trying to detect these gravity waves are by using these very small, incredibly dense, highly magnetized stars called pulsars. Basically what a pulsar is, it's, as I've said, very small and dense, roughly the size of a city, having the mass of up to 2 suns packed into that space. And what makes pulsars unique is that they have beams of electromagnetic radiation spewing out from their magnetic poles. And as the pulsar rotates around its axis, the magnetic pole, which is displaced, sweeps across the sky like a lighthouse. And once the lighthouse beam intercepts Earth, we receive this pulse of electromagnetic radiation. And by precisely measuring the time that these pulses arrive, we can, down to like tens of nanoseconds in precision level, we hope to be able to detect gravitational waves which will manifest as slight variations in this arrival time.
Of course, there are a lot of problems with this sort of measurement because what we're looking at are pulsars which are between 1 and 4 kiloparsecs away, which is thousands of light years. And what that means is that there are lots of sources of error that will kind of obstruct the signal that we're trying to get from the pulsar, data, that's minute variations. And so we get a lot of noise, and what we particularly focus on at Oberlin is interstellar medium. Interstellar medium is the ionized plasma between us and the pulsar and between all things in space. What it does is it diffracts and scatters the pulses that occur because it is ionized and our waves are electromagnetic waves. This causes them to have diffraction gratings and different path lengths. This causes a lot of noise and really limits the amount to which we can precisely detect these pulses and therefore gravitational waves.
All right, so after the original pulse is scattered by the interstellar medium, it arrives at Earth looking something like this. This is a dynamic spectrum, a grayscale of the pulse, where the darker points are where the pulse intensity is stronger and the lighter points are where it's weaker. We took data from one pulsar over the course of about an hour over a 10 megahertz frequency band. And as you can see, there's this crisscross hatching pattern indicating that there's some sort of correlation between the data. But after the...
One of the reasons that these don't appear as straight lines in the dynamic spectrum is because the effect of interstellar medium is frequency dependent. And while that does introduce a really tricky element, it's also great for analyzing interstellar medium because we can take the 2D Fourier transform of our dynamic spectrum and get this really nice parabola that shows the relationship between the frequency and the time delay that we're getting. And so when we look at this, we see that it closely fits a model where we do have a single screen, which is what we're trying to use to model. And from this parabola, we get this equation for the curvature of our parabola. And in fact, it relates the Fourier transform to distance to the pulsar, effective velocity of the pulsar in the Earth, and the distance of the screen.
So in order to complete the equation, we needed to get the velocity of the pulsar at any given time. So we needed so we constructed an equation that accounts for the rotation of the Earth around the sun. And from that we can get the velocity of the line between the pulse and the Earth as it moves through the interstellar medium in the screen. And it created this beautiful little graph here where you can see the motion of the pulsar across the sky mixed with the orbit of the Earth around the sun that creates the squiggles in it.
Once we model the velocity of our line of sight, we then are able to calculate our S values from the known distance and other known variables, including observation wavelength. And what we get currently is 2 values of S. This is because with relation to our S, our equation is quadratic. And we also, for each S value, we get an evolution of S over psi. Psi is an additional element in our curvature that is due to the smeared or elongated image of the pulsar in the sky due to these interstellar medium effects. What we hope to do in the future is to accurately get psi, so we'll get a single value of S instead of this evolution, and we hope to work to eliminate one of these measurements of S. That way we know a precise location of S. Once we do that, we're able to more fully understand the effects that this has on the arriving pulsar time and pulsar beam, and hopefully use this to address the problem of interstellar medium and detecting gravitational waves. Thank you for listening.
Yeah.